Very important. All right. Now, when you have um, extensional stress, okay, and I want you to listen. I want you to listen. When you have extensional stress act on a pre-existing rock, remember we talked about, you know, layering the last time, right? Undeformed sequence of rock, and you have extensional stress act on that undeformed layer. What you initially get is a thinning of the crust, a thinning of the crust. With continual extension on that undeformed layer, or the layer that is becoming deformed, you then begin to get what you call fractures. And fracture simply means, you know, um, the discontinuity in rocks, okay, where you now have two free faces, two free faces. That is a fracture, all right? There are two types of fractures. The first one is called a joint, a joint. So a joint are fracture beds or bedrock along which you don't have any sort of movement. That is the first type of fracture. All right. They form at shallow depths, the characteristics of a joint. They form at shallow depths in the crust where the rocks break in a brittle way and is slightly pulled apart by what? Tensional stresses. And this was exactly what I was trying to let you guys understand just now. All right. So, what kind of stress would form fracture? It's extensional or tensional stresses. All right. Please take note of this, extensional stresses. They will lead to what we call fracture. Okay. And then a type of fracture that could form is a joint. All right. So a joint essentially is a fracture with relatively little or no displacement, all right, of the blocks. Do we understand what I'm talking about?
Yes, sir.
All right. So there's little or no displacement. Okay, little or no displacement. Abdul Latif, you are not under any pressure to respond as the class captain. All right. uh, you've got other people here. If they want to respond, fine. If you guys don't want to respond, it's okay. We can always move on. If I ask a question, I want you guys to respond and let this class be interactive. That's the only way you will learn. All right. We're saying joint is the first type of fracture, number one. Okay. And they are characterized by relatively little or no displacement along the um, uh, fracture. Okay. Um, they are caused by bending or regional uplift. Okay. Essentially, that is characterized by tensional stresses. Okay. And then when you have multiple joints, they form joint sets. Joint sets. Here is an example to the right of this figure is an example that shows us um, a vertical joint in a sedimentary rock at Moab in Utah in the United States. And all of this is in response to what we call tectonic uplift of the region. So what you see here are vertical joints, and you can tell these are vertical joints that are aligned in this orientation. Okay, you can see how they are aligned. On here, you see that these joints, right, they've not been moved or displaced um, largely. All right, they are just signifying breakage in the rock. All right, so joints are a type of fracture along which there's little or no displacement on the rock. And then when you have multiple joints, you call them you call them joint sets, multiple parallel joints. Okay, they are associated with both uplift and vertical compression and stress. Okay, so what you see here, the red arrow is suggesting uplift. Okay, and then you see different joints that makes up, the joint set on here. All right, so you can see some that are oriented in this direction. You can see some that are oriented in this direction. Okay, so please take note of that. So that is joint set. Okay, so joints can be systematic or non-systematic. They are systematic when you have them being parallel, and then they are defined by straight uh, uh, orientation like this, and they are parallel to each other. Okay, a non-systematic joint is defined by the curved geometry and it's not being parallel to one another. All right, a non-systematic and then a systematic joint. All right. Why are joints important? They're important because they could contain valuable ore deposits, okay? And that is because they are zones of weakness in rocks that can be exploited by um, migrating solution, hydrothermal solution, that will eventually form important ore mineral deposits, such as gold, copper, silver, and zinc. Okay, so they can contain valuable ore mineral deposits, including all of this. All right, and then they're important because of engineering projects. All right, so we need to know where joints are in the subsurface so that we can aid our planning and construction of engineering projects. The third reason is that it controls the movement of contaminated water from abandoned mines. So they can act as conduits for the transportation of either hydrothermal fluids or groundwater from abandoned mines. All right, that is why they're important. The second type of fracture is called what? Faults. And faults, right, are basically discontinuities in rocks that along which there's been some relative movement of the blocks. Relative movement of the blocks. That is a fault. All right. So that displacement could be several centimeters, hundreds of kilometers. All right. So each fault is unique because they can be displaced just by little distance or by several distances in kilometers. Okay. The contact may be narrow or may be made of broken, pulverized mass sandwiched between the displaced sides. So, for instance, what you see on the screen here, it's a fault zone, okay, and this is the fault zone highlighted in this red patch, if you like, okay. So that is a fault zone, all right, a fault zone. And you can see the schematic drawing here. What you see here, you can see that there's an arrow going down here, another arrow going up. Can you see that? Can you see that?
Yes, sir.
All right. So this, so if you try to, if you try to draw on, um, just a sec. If I raise this, and I try to draw on what you see here, okay, I'll come back here and I'll take this. So this bed here, if you just follow me, what I'm doing here, all right, could possibly be this bed here. And we're looking at the color to say this essentially. And you can see how it has been displaced, okay, by this zone here. Can you see that? And that's what has been drawn here. So this bed has gone, or this block on this other side has gone up relative to this one here. Can you all see this?
Yes, sir.
All right. So we said a fracture is a discontinuity in rock. We said there are two types. The first type is what?
Joint.
Joints, all right, where there's little or no displacement. And the second type is a fault, all right, where you have relative displacement um, between the blocks, all right, such as you have here, all right, such as you have here. So this is the fourth zone, fourth zone. But at other times, instead of a zone, what you get would be a fourth plane, all right? So something like this. So if I were to draw this as a displacement, these two blocks that has been displaced uh, by a plane rather than a zone, you're going to get something like this. You're going to get something like this. So not all the time you get, not all the time you get a zone that defines the contact of the fault. Can you see this? All right. So you understand what's going on here. So this, formally, you would have these two rocks or these two bodies be this. Okay. So this is before. Okay. This is before. And this is after. Okay. You can see how the rock has been displaced up this side, and then this side is been displaced down. Now, having known the definition of a fault, we said the fault is a discontinued rock along which there's been what displacement of the blocks, right? Good. Or relative movement of the blocks. Now, what are the types of faults? Look at this diagram. Geologists describe fault movement in terms of the direction of slippage. All right, direction of slippage. So you have a deep slip fault, all right? Now, these are not the types. These are not the types generally. This is kind of the category, all right? So they describe fault movement in terms of the direction of slippage. So you could have a deep slip fault, a deep slip fault. So these two diagrams here, 1 and 2, all right? 1 and 2 talks about deep slip faults. Okay? Why is it deep sleep? It is called deep sleep because the movement is parallel, right, to the deep of the fault. What is the deep of the fault? We talked about deep already in our last class, right? This is the deep of the fault, right? The deep of the fault. Let's assume you have a free face here. Let me draw a free face here. So this is in 3D. Okay? This is in 3D. Excuse me. This is in 3D, right? This is the strike direction. Okay? And this is the deep direction. All right? As you can see, this 1 and 2 fault here, reverse and normal fault, all right, you can see they are oriented in the deep direction, irrespective of the movement of the blocks. All right. And then the strike fault is oriented in the strike direction. And then there is the oblique slip fault that is oriented
Can hanging wall block above fault?
above the fault or above the fault plane.
Above the fault plane.
Hello?
Guys, sir.
I'm going. Can you guys hear me?
Yes, sir.
Yes, sir.
I'm just trying to. Okay. Just a quick word. I see that some of you are distracted. Imagine someone is pricing phone. I don't know what the person is pricing. I don't know. You are supposed to be here. You are supposed to be 100% here, trying to understand, these concepts. But I don't know. You guys are playing. Some of you, not all. I mean, some. All right. I want to encourage you. All right. Some people failed this course last year. I don't want you to be part of them. All right. I don't want you to be part of them. So concentrate. When it's time for this course, you come, you sit down, you listen, listen up, follow the explanation so that you can at least answer questions when you see them in the exam. All right. The word is enough for the wise. All right. So before we went off, we're trying to differentiate between these various categories of rock, especially for the deep sleep fault. And we said for deep sleep fault, you can either have a reverse fault and a normal fault. And I was asking a question: what is the difference between a reverse fault and a normal fault? Can someone tell me, please?
Good morning, sir.
Good morning.
The difference between a reverse fault and a normal fault is that the reverse fault happens when the hanging wall moves up relative to the footwall, while the normal fault is when the hanging wall moves down.
You are absolutely spot on. And I like that. I like people to listen. All right. And both types of faults are examples of what? A deep sleep fault. Deep sleep fault. That is excellent. Thank you very much. Who was that, please? I can see Fumi.
William, sir.
Okay. Williams. Fumi. Williams is your surname, right?
Yes, sir.
All right. Fumi is your name. All right. Good. Your first name. Okay. So that is one category. Now, think about the second category here that talks about strike slip fault, all right? And you knew before we went off that I drew a schematic. You only have this horizontal component, all right, of movement, all right? It's not like the deep sleep while we had the movement being parallel to the deep direction. Now the movement is perpendicular to the deep direction, and that's why it's called a strike slip fault. So the movement is predominantly horizontal and then parallel to the strike of the fault plane, as you can see here. And that is why it is called a strike slip fault. And then, for the oblique slip, like I already told you, you've got both vertical and horizontal components of movement, like you see already illustrated in this diagram. You've got both vertical and horizontal. That is an oblique slip fault. So this is just to tell you or describe faults in terms of the direction of slippage of the fault. All right. Now, ordinarily, okay, if you're asked, the different types of faults, you'll go with number 1, normal, number 2, reverse, number 3, strike slip fault. So generally, all right, generic classification of faults involve both the normal, the reverse, and the strike slip fault. But when we now talk about the direction of slippage, you can then say a deep slip, strike slip, and oblique slip. I don't know if you understand what I mean. If we're talking about types of faults, there are 3 types: normal, reverse, and strike slip faults. But when you now say, what are the types of faults in terms of the direction of slippage, you want to now then illustrate deep slip, strike slip, and oblique slip faults. Does that make sense to you?
Yes, sir.
All right. So in terms of slippage, there are 3 types. Okay. Now let's think about normal faults. All right. So what we said in the previous slide, the hanging wall has moved down relative to the foot wall. All right. And that is due to extensional stress. All right. So extensional stress will cause a normal fault. Okay. So again, you can see the hanging wall, right? In this example here, the hanging wall has moved down relative to the foot wall. So this is D and this is U, telling us which block has moved up and which has moved down. So sometimes in the field, what you will get is that you will get, can you see a block diagram here that has been sort of eroded? So you can possibly get all of these beats eroded, right, in the field. And then what you're left with is this kind of geometry. So all of this would have been eroded out, okay? So your job as a geologist is to determine which block has gone up or displaced downwards. Okay. Now this normal fault is due to what? Extensional stress. So on this arrow, you can see, the arrow is telling us that this rock body, right, or this layer has been pulled apart. Okay. And then you can have various types of features in an extensional setting. All right. Apart from normal fault, you can have structures like graben and horsts. What that simply means is that when you have a pair of conjugate normal faults, you can have some block, right, down faulted, like you have here. Can you see a pair of conjugate normal faults? Can you see this is a normal fault? Okay, and this is also a normal fault. So it's a pair. And because it's a pair with continuous extension, you're going to have this block 2, this is block 1, block 3, right? Down faulted. All right. When it's down faulted, you get what you call a graben. So a graben is a down faulted block in an extensional setting. And the opposite of that is a horst, all right, which is up faulted. Same setting, right? But you can see that this is up faulted. And that has to do with the orientation of the normal faults. The orientation of the normal fault. Okay? So you can have, yeah, Benedict, you want to ask a question? Go ahead. You want to go ahead? All right. Okay, so I was talking about other features you can get as an extension of setting, and I said that it's possible to get what you call grabbing. What is a grabbing again? Who can remind me? What is a grabbing?
A down-folded block. Sorry, one.
Okay,
Go on.
a down-faulted block. Why the host is what?
Up-faulted block.
Is the up-faulted, as you can see. The opposite of the grabbing is up-faulted, while the down-faulted is a grabbing. All right, and I've said that it's possible for you to get this fault scarp, okay, eroded, and then you're left with more or less like a surface, an eroded surface that won't give you a clue as to what's happening in the subsurface. But your job is to then figure out which one is which of the block has moved up relative to the footwall or down relative to the footwall. All right. So all of this you want to represent on a map. You want to represent on a map. All right. And I believe my colleague will take you through that. And then the other question is, about hanging wall and footwall. Okay. That word was coined from, miners. All right. So you can see hanging wall block, footwall block, and you can see this is a mine, and you can see one of those workers in there with a lantern. All right. So the same picture has been enlarged here, and you can see it's carrying a lantern. You can see the relationship between the hanging wall and the footwall of a block is shown here on this picture. The upper surface where miners can hang a lantern is the hanging wall. So that's where the name came from. The upper surface where you can hang a lantern is the hanging wall. The miner's feet, okay, are on the lower surface below the footwall. Okay. So if you can hang a lantern here, that will be the hanging block. And where you're stepping on, all right, will be the footwall. And this is the ore. This is the ore body there. Okay. But then that is from the miner's perspective. Okay. But I'm just telling you that the hanging wall always rests on the fourth plane. So please take note of that. And the footwall is below the fourth plane. Very important. All right. We're making progress. So the features of a normal fault, we've talked about grabbing. Okay. There are fault blocks that are bound by normal fault that are down or drop down. Okay. Down faulted. The host, okay, is a fault block that are bounded by normal faults that are uplifted, upthrown. Okay. And here is from Southern Oregon. Okay. And you can clearly see, and from the schematic here, you can see that this block has moved up relative to this one. You know that because when you try to trace the bed, you can clearly see that there's been some sort of displacement on the beds. Okay? Displacement on the beds. All right? So I want you to take note of that as you read through the notes. Very important. Okay, so this typifies, so this is the fourth, and this is the fourth plane. Okay, and that's exactly the same diagram you see here. All right, so this is host. So these are not fictitious terminologies, they actually exist. And this is a road cut exposing the host structure. All right, this one here. You can also have grabbing. So this is the same diagram from previous, and then grabbing and host. Together, the grabbing and host, all right, make up what we call a rift system. A rift system. These are grabbings associated with what? A divergent plate boundary, all right? And you can see the arrows telling us that, in fact, extensional tectonics is taking place. Extensional tectonics will give you what we call host and grabbing and half grabbing structures, all right? So when you see just a section of this preserved, such as you have here, okay, it's called half grabbing, half grabbing. So grabbing, half grabbing, host structures, all of those are example features of a rift system where you have extension taking place, all right? So you have normal faults, grabbings, half grabbings, host structures, characteristic of a rift system. All right. Now, let's think about reverse fault. A reverse fault will form in a compressive regime, not an extensional regime. So you see the arrows pushing against the rocks, okay? Now, who can tell me the difference between a reverse fault and a normal fault? Who can tell me the difference? Who can tell me the difference between a normal fault and a reverse fault?
So in a normal fault, the hanging wall is going downwards, while in a reverse fault, the hanging wall is going upwards.
Good. So you can see that the hanging wall has been displaced up, okay, relative to the foot wall. That is a reverse fault. All right. And then we have a variation of that called a truss fault. Okay. For truss faults, all right, they are reverse faults which deep angles is less than what? 30 degrees on the horizontal. So this is a reverse fault. And you can see this fault here is at an high angle. Now, when this angle here, okay, is less than 30 degrees, you're going to have something like this. Oh, sorry. You're going to have, ignore that. You're going to have something like this. Okay? You're going to have something like this. All right, so this is the hanging wall, and this is the foot wall. All right, so when you have an angle that is 30 degrees or less, that becomes a truss fault. A truss fault. This is at an high angle, and this is 30 degrees or less. So a truss fault is a reverse fault that has an angle with the horizontal that is 30 degrees or less. Okay, 30 degrees or less. And here's another example of, a reverse fault in Southern Oregon. All right, Southern Oregon. So this is the hanging wall, and this is the foot wall. This is an example of a truss fault, okay, of a truss fault because the angle is a lot shallower, okay, and then this is the surface trace of the fault. Now, it's possible for you to have this upper part eroded, and I'm saying all of this because when you begin to map these faults in the field, right, this is what you get when you begin to map them in the field. This is a truss fault because the hanging wall has moved up related to the foot wall, and this is the fault trace on the surface. All right. So we've talked about normal faults and we've talked about truss faults. Now you understand what the hanging wall is and the foot wall is, okay, and how they relate to these two types of faults. Yes or no?
Yes, sir.
All right.
Yes, sir.
Good. We're on the same page, right? So I need to move ahead. Look at this diagram here. All right. This area is called the Chief Mountain in Glacier National Park in Montana. Okay. And that is an erosional remnant of a major thrust fault. What is a thrust fault again? Who can remind me what a thrust fault is?
It's a reverse fault.
Just what is a reverse fault that has an angle that is 30
Angle of less
degrees or
than
less.
30 degrees.
30 degrees or less.
30 degrees or less. Okay. Look at this area here. And this is the interpretation of what is going on here. So you have a thrust fault that runs, okay, that runs all along, right, this area here. Okay. So all of this unit here, okay, has been brought up. Okay. So this is the hanging wall, if you like. Okay. And this is the what? The foot wall. Okay. So it has been moved this distance. And this is called the Lewis thrust fault, because obviously you have a shallower angle fault. Okay. And then the hanging wall has moved up relative to the foot wall. Okay. This is a real life example. All right. Please take note of that. And last but not the least, you have what you call strike slip faults. Okay. For this kind of fault, right, you've got movement predominantly in the horizontal direction, and it is parallel to the strike of the fault plane. All right, to the strike of the fault plane. If you try to reconstruct, okay, what you see on the screen, you can see that the red arrows are telling us the sense of movement of along this fault here. Okay. In fact, they suggest that it has moved, and that if you try to reconstruct this, okay, it has moved a distance. Same thing you see on this diagram here. Okay. Where you have horizontal movement, okay, along, so there's a fault that is running across here. All right. And in fact, has been displaced by that movement. Okay. So please take note of what a strike slip fault is all about. Now, there are two types of strike slip fault depending on the viewer of that fault. Remember, we said the movement is largely horizontal and parallel to the strike of the fault plane. Okay. Now, let's assume you are the viewer and you stand here. All right. You stand here. And then you are the observer, right? And you look at this fault this way. If the right block is coming towards you like this, right? It is called right lateral. Right? What? Lateral. What that simply means, another word for that is called what? Destral. Destral fault. Destral. Okay? Right lateral destral. Because the right block is coming. You can see that this is a strike slip because you have movement in the horizontal that is parallel to the strike of the fault plane. All right? You can see that this channel here has been displaced quite a distance. Okay? So this is right lateral. Now, if you're the observer here, all right, and the left block, okay, this is just, okay, let's stay with right lateral because it's the same figure. What this is telling us here is that you can see the difference between these two diagrams. You have a linear strike slip fault here. So the fault here is straight. But at other cases, instead of you to have a straight fault plane, what we usually have will be bends right, in the fault. I don't know if you can see what I'm trying to draw here. Can you see that? Hello?
Yes, sir. But I don't
So
understand, sir.
When you have bends, I'm trying to draw. So this here is a straight fault plane. Yes or no? Can you see that?
Yes, sir.
But here, you can see that this fault plane is not straight.
It's kind of cool.
It's curved. And that was what I was trying to illustrate here. Now, imagine, let's think about the sense of movement of the two blocks on both sides of this fault. Let's assume that this block is going in this direction. And this one is coming in this direction. Okay? Think about what will go on here, right? You're going to have opening here and here. And then you're going to have closing here and here. And that's when you have movement along the fault. Is that true, yes or no? You're going to have this kind of opening here because of the curve on the fault plane. And then here will be closing. This opening is called a releasing bend. And that's because the fault plane is not straight. The fault plane is curved. So here you're going to have an opening because of the sense of movement of the blocks on either sides of the strike slip fault. And then here you're going to have closing because of the sense of movement of the block. This closing you have here is called a restraining bend. So along a strike slip fault, depending on whether it is linear or curved, whether you have bends on the fault, you're going to have what you call a releasing bend or a restraining bend. Now, please take note of that. The other point I want to bring to your notice is what we call the opposite of the right lateral fault. So for instance, you were observing the fault, all right, and it was the left block that was coming towards you. So I'll draw this again, say the left block was the block that was coming towards the viewer. Okay? And in fact, the right block was going away from the viewer. Okay? And you are the observer. And you're trying to observe this rock. You can see that the left block is clearly coming towards you, and this right block is going away from you. This is what we call left lateral. You can see it's the opposite of what is going on here. The left lateral strike slip fault is also called sinistral. Sinistral. Do we know the two types of strike slip fault now?
Yes, sir.
Good. You have dextral sinistral or right lateral and left lateral strike slip fault. Depending, right, on the observer. All right. This is the last slide. Let's think about what's going on here. The California greatest fault is the San Andres fault. The San Andres fault is a strike slip fault. Okay? And it's a strike slip fault. And look at the location here. All right? This is the location of the San Andres fault. This is the North American plate, tectonic plate, and this is the Pacific plate. So along this plate boundary, there is a strike slip fault. Okay? that shows that there's been relative displacement of the Pacific plate against the North American plate, and is a famous worldwide example for a strike slip fault, and that fault is called the San Andreas fault. All right. Again, we can see the surface trace of this fault, and this fault has been studied several times. Segments of the fault have been, studied by several authors over the years. Okay, it's famous because you've got various tectonic activities happening along this fault. For example, earthquakes. Okay. All right. What have we learned today? We've basically talked about structures that are formed by both extensional and compressional tectonics. All right. We've talked about fractures forming from extension, and that fractures are discontinuity in rocks. Not only that, we said fractures can be divided into two types. We said you've got joints, in which you have relatively little or no displacement across the free surfaces. Remember, you have a single block, and then when you have a discontinuity, you now have two free blocks with two free faces. All right. So you've got little or no displacement in joints, but in faults, which is a second type of fracture, you have two blocks that have been relatively displaced. We say in terms of the direction of slippage, you can have a deep slip, a strike slip, or an oblique slip fault. For a deep slip, the movement of the fault is parallel to the dip of the fault plane. While for a strike slip fault, the movement is parallel to the strike of the fault plane. And then when you have both dip and strike components to the movement, that is called an oblique slip fault. There are three types of fault. Normal fault, all right, where the hanging wall has moved down relative to the foot wall, okay, formed by extensional stress. Thrust fault or reverse fault, where the hanging wall has moved up relative to the foot wall, okay, in a compressional setting. And then strike slip fault, where one block has moved past another in an horizontal sense, okay, and that is caused by what we call sharing of the blocks, or sharing stress, if you like. Now, we said there are other features that are associated with extensional landscapes, including grabbing, half grabbing, and horse structures, all right, that are related to normal faults. All right, we talked about that. We said a modification of reverse fault is a thrust fault that has an angle, that makes an angle with the horizontal that is 30 degrees or less. And then we also talked about two variations of the strike slip fault, including what? Tell me. What are the types of strike slip fault?
The right lateral and the left lateral.
What is another name for right lateral?
Dextral.
And what's another name for left lateral?
Sinistral, sir.
Sinistral. All right.
Yes.
I hope you understand this. I hope you understand this.
Yes,
Yes,
sir.
sir.
All right.
Yes, sir.
Let
Sir,
me,
excuse me, sir.
yes, talk to me.
Can you come again with the other name for right lateral set?
Right lateral is called dextral. 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 Can you see my screen?
Okay, okay, sir. Thanks, sir.
Dextral. And then the left lateral is called sinistral. Just a sec. I'll stop sharing many minutes do we have left here? I'll stop sharing. I want to pull up a note. I want to see. I want to pull up a note here. Just a sec.